So, again, in our series of lectures, we're going to be starting a new topic, work and energy. And this is going to be one of the fundamental topics in the entire year-long physics sequence, not just this semester. The idea of energy is something that we'll be using time and again for the rest of the term. So let's make sure we understand it. And we're going to start by examining the concept of work. Now, what is work in the physics context? Let's start by using the kind of common everyday idea behind work. The amount of work done is the same as the effort that is done. Now, you put effort into something, you've done work. But we're going to have to be careful because we need to be more precise than what I just stated in order to understand work. Specifically, we're going to find that we need to discuss doing work on something. To get a start on that idea, we're going to use a hockey puck. Using a hockey puck, I don't want you thinking about friction. We're not, on a horizontal surface, so we're not worrying about gravity interfering with things. So the only thing that's going to affect the puck is the effect of the stick pushing on it. If the puck is initially stationary, if it has no speed, and you push on it with a stick, it's going to start speeding up. It's going to start moving. And if you take that force and push the puck just a short distance, when you're done, the puck is sliding across the ice at a relatively slow pace. But if you take that same force and you push on the puck for longer, by the time you're done pushing, the puck has a greater speed. Furthermore, you can tap the puck, or you can strike it very hard. If you tap the puck, you're giving it a light force and it has only a small speed. But if you strike the puck very hard, you're doing so with a large force, and when you're done, the puck is going to have a high speed. And those two ideas, that the force applied can affect the speed, and that the distance over which the force is applied can affect the speed, those are the two things that go into determining work. You see that equation at the bottom of the screen? Don't commit that equation to memory or anything because we're going to modify it. But it gives us our first introduction to the idea of work. Work equals force times change in displacement. But notice the sentence above it. Our first equation for the calculation of work done on an object is. There is a very important word there, and it is the word on. The work done on an object. That is what we concern ourselves with when we talk about work. The work done on an object. Not the work done by the force, but the work that the force does on an object. So what do I mean by that? If you are doing a whole lot of work and you are perspiring by the end, that doesn't necessarily mean anything. The question is, what did you do work on? How did the thing on which you were working change? So it's not the agent doing the work, it is the thing on which the work is being done that's important. A very important distinction, and I hope that over the course of this lecture, that distinction gets driven home. Couple of questions. So the equation depends on distance and not on time? Okay, why? Because by definition, the work is the work done on something. If nothing changes about that something, if it stays in place, no work is done on it. You can push and push and push against a wall. That wall doesn't move, you've done zero work on the wall, no matter how achy your muscles are after you're done. That's not the important thing as far as work in physics is concerned. How did the motion of the thing on which you are pushing change? How does that motion change? delta x instead of distance? Why change in displacement instead of distance? Because change in displacement could be negative. Does that mean that work can be negative? And the answer is yes. Work done on an object can be negative. How do you know whether work can be positive or whether it can be negative? If you're working to speed something up, you're trying to do positive work on it. If you're working to slow something down, you're trying to do negative work on something. A force that is acting to slow something down is doing negative work. A force that is acting to speed something up is doing positive work. Furthermore, we can also look at the relative directions between the change in displacement and the force. If the change in displacement and the force are in the same direction, both positive or both negative, then the force is trying to speed things up. It is doing positive work. If the force and the change in displacement are in opposite directions, that means, for instance, that the object is moving to the right, but the force is to the left. The force is trying to slow it down. If they are in opposite directions, the work done by that force is negative. Make sure you understand that. If delta x and f are in the same direction, whether both positive or both negative, the work done is positive. If delta x and f are in opposite directions, the work done by that force on the object is negative. Understand that. That will help you understand the theorem. Yes, there is a physics theorem that goes along with it. The nice thing about this physics theorem, I'm not going to force you to memorize a formal proof. I'm just going to state what the theorem is, and then we'll look at the consequences of that theorem. What are the units for work? Units of force times units of displacement would be newtons times meters, but that combination has been named after an English scientist of the first half of the 19th century, James Prescott Joule, Joule, and the unit is abbreviated with a capital J. 1 joule equals 1 newton times meter, and in fact, 1 joule is also equal to a kilogram times a meter squared per second squared. And I referred to F equals delta X as the first equation. Like I said before, we are going to modify it to something that is more accurate and more useful. Finally, in these questions, is work a vector quantity or is it a scalar quantity? And work is actually a work is actually a scalar quantity. Now that means it doesn't have a direction. You can push something to the left and we say the work is done on, you do work on it, you push it to the right, we say work is done on it. We don't say work to the left, we don't say work to the right, we don't say work up, we don't say work down. And not only is it without a direction, it could be a positive quantity or a negative quantity. And you might think, that sounds a little crazy. If it's negative, doesn't that mean in the left or right, or, down or something? And the answer is no. As kind of an example of something that inherently doesn't have a direction but could be positive or could be negative, think of your bank account. Certainly we want to have a positive bank account, but it doesn't mean that you can't have a negative account. There might be negative dollars in your account. There's no direction associated with that. It's not a vector quantity, and work is like that. There's no direction associated with it. Positive work is trying to speed up something. Negative work is trying to slow down something, regardless of the direction of that something. Let's do a quick example with the hockey puck. So a goalie applies a horizontal force of 32 newtons, and while the stick is in contact with the puck over a distance of 0.64 meters. how much work was done on the hockey puck. And this is as straightforward as you can get. Horizontal force, the puck is moving in the same direction that the force is being applied. So we're going to be doing positive work. The magnitude of the force is 32 newtons. The change in displacement has a magnitude of 0.64 meters. We just multiply those two quantities. And as I said, since it's being done to speed the puck up, the work done is positive, 20.48 joules. Now, a couple of questions to make sure you understand the idea that if the work and the change in displacement, if the force and the change in displacement are in the same direction, the work is positive, and if the force and the change in displacement are in opposite directions, the work is negative. Consider the following scenario. We have an object falling to the ground, just free falling straight to the ground. What can we say about the work done by the gravitational force while the object is falling to the ground? Is that work positive? Is that work negative? Is that work zero? Next question. We're taking this object and we're tossing it straight up into the air. And while it's on its way up, what can we say about the work done by the gravitational force? Is it positive? Is it negative? Or is it zero? Think about these. Think about the idea that if the change in displacement and the work are in the same direction, the work is positive. If the change in displacement and the force are in opposite directions, the work is negative. We're looking at the situation of a purely horizontal force acting on that puck to move it across a horizontal surface. What if that force isn't purely horizontal? For instance, I could come along to a table and I can push straight down on that table. The table, of course, sitting on the floor would only be able to move horizontally, but my force is straight down. Do I do any work on it? Well, the table doesn't move. I do zero work on it, but we can put that into a mathematical formula, and we're going to modify our expression for work to come up with a better equation for the work done. In the figure you see on the screen, we have an object on a horizontal surface, and we have a force that is not purely horizontal. The force makes an angle of theta with respect to the horizontal. And there's a component of the force that's to the right, which is the direction the object moves, and there's a component of the force that is straight down, which is not exactly perpendicular. It is perpendicular to the direction in which the object moves. It's the component of the equation parallel to the direction of motion that counts. The vertical component of that force does no work, but the horizontal component of that pushing force does work. And the horizontal component of that pushing force is the magnitude of the force times the cosine of the angle it makes with respect to the positive x-axis, which we assume is to the right. So this pushing force, the work it does is based on the component of the force parallel to the direction of motion. And in equation format, we typically state that as the magnitude of the force times the cosine of the angle. Theta. Let's get a little bit more formal about our understanding of theta. Theta is the angle between the direction of motion and the direction of the force. Theta is the angle between the change in displacement and the force. Those are equivalent statements. The angle between the change in displacement and the force, that's what goes into that formula. That's what theta represents. So could we say that work is equal to force times change in displacement times cosine theta? No, but it's better. And we're going to do an example. Let's say we have a 43 kilogram cart represented by the yellow rectangle. and we're pulling it across a horizontal, frictionless surface. The force is being applied through a rope, so we have a tension force, and the direction of this force is 24 degrees above the horizontal, and it has a strength of 51 newtons. So some person pulls on the cart via this rope. How much work is done by this person if they pull with a consistent force for 6 seconds? With a consistent 51 Newton force for 6 seconds. Okay, we're going to actually have to go back to some kinematics here. We want to figure out the distance, the change in displacement that the cart travels. We're given the force, we're given the angle. We know F, we know theta, we need delta X. How are we going to get delta X? Well, we know it's initially at rest, and we know for how long it's moving. We know that there's an applied force, so there must be an acceleration. We're going to have to do some one-dimensional kinematics to get what the change in displacement is, but in order to do one-dimensional kinematics, we need to find the acceleration. And to find the acceleration, we're going to have to do a Newton's second law analysis of this cart. So we got the whole thing going on here. We have this new concept of work. We have our concept from early in the semester about kinematics, and we have our concept about force and Newton's laws of motion. Let's get going. The only direction of motion is, the direction of motion is purely horizontal. We're only going to worry about the x direction. And so I know all of these angles. So the pulling force times the cosine of 24 plus the normal force times the cosine of 90 plus the gravitational force times the cosine of 270. The cosine of 90 is 0. The cosine of 270 is 0. We are left with the pulling force of 51 newtons times the cosine of 24. Hey, I can plug that in. And I get 46.6 newtons. So the net force acting on this cart is 46.6 newtons to the right. That's going to be equal to mass times acceleration. Newton's second law, net force equals ma. So 46.6 newtons equals ma, and the mass given is 43 kilograms. So 46.6 equals 43a. A equals 46.6 divided by 43. The acceleration is 1.084 meters per second squared. So we got that. Now we can apply some one-dimensional kinematics to figure out what the change in displacement is over 6 seconds. So x final minus x initial is equal to delta x. So I can rewrite that equation, delta x equals v initial t plus 1/2 at squared. The cart is initially at rest, so v initial is 0. That allows us to say that delta x is 1/2 at squared. And we just found a, and we're given t. We plug them in, and the change in displacement is 19.512 meters. Finally, we can calculate the work. The work is equal to the force times the change in displacement times the cosine of the angle between the force and the change in displacement. The force is 51 newtons. The change in displacement we just calculated as 19.512 meters, and the angle theta is 24 degrees. Plug it all in, and you get that the total work done is 909 joules. Quick conceptual question for you. We have a satellite in a perfectly circular orbit about the Earth's center. So it's out in space. The center of its circular orbit is the center of the Earth. What can we say about the work done by gravity on that satellite? And you see several different formulas. Capital G, the mass times the mass of the Earth divided by the radius of the orbit, minus capital G times the mass of the Earth divided by the radius of the orbit, capital G times the mass of the Earth divided by the square of the radius of the orbit, or 0. Think about it. you're not sure, don't hesitate to ask a question in class next time. Up until now, we've only formally considered really only one force acting on the object that is affecting its motion. Certainly in the cart problem, we had the normal force and the gravitational force, and if we were going back to looking at the puck, there's a normal force and a gravitational force, but they weren't directly affecting the motion because they were perpendicular to the direction of motion. But what if we had several forces which have components that are parallel to the direction of the motion? Well, what do? We got to add up all of the separate works done. So that would seem to indicate that we might want to say that our total work is equal to the work done by the first force, F1 delta x cosine theta 1, plus the work done by the second force, F2 delta x cosine theta 2, plus the work done by the third force, F3 delta x cosine theta 3. Is this the final equation for work? Well, no, but it's pretty good for this course. This expression doesn't take into account the possibility of the force being anything other than a constant, both in magnitude and direction. So the actual equation is more complicated and it involves calculus, integrals, to be honest. We're not touching that. So what you see on the screen is more or less what you got to worry about. But let's also look at it a slightly different way. You can calculate the work done by the first force. You can calculate the work done by the second force. You can calculate the work done by the third force, etc. And then the total work done is the sum of all those, the work done by all of those forces. So, too long, didn't read. Our best equation for the net work done is that it's equal to the sum of the separate works done. But I could talk about the net work done as being equal to the net force times the change in displacement times the cosine of the angle between the change in displacement and the net force. That's what theta net represents, the angle between delta x and F net. I think that the top equation is best. It involves having to calculate the work done by the first force, the work done by the second force, the work done by the third force, and then adding them up. And what you see in this very bottom equation is kind of that idea. The work done by the first force plus the work done by the second force plus the work done by the third force. Just find them and add them up. Now, let's see. When we talked about work done on an object, and we referred to the hockey puck, we talked about the speed of the puck changing. Is there a speed-related property that has units of joules? If I want to make a direct comparison between the work done and the actual motion of the object on which the work is done, is there a direct comparison? Is there a quantity associated with the object that I can say the work changed to this quantity? It can't be just speed. Speed has units of meters per second, work has units of joules. I can't directly say if I do 20 joules of work, this changes by 20 meters per second. Nope, does not work that way. There's a different quantity. That quantity is called kinetic energy. It's like the energy associated with motion. There's a derivation on the screen. Don't copy this down. I include the derivation for the sake of completeness, mostly to show you that the expression for kinetic energy isn't just some sort of made-up thing. There is an actual derivation, even more formal than this, that explains why kinetic energy is 1/2 mv squared. But that is our formula for kinetic energy. The kinetic energy of an object is 1/2 times the mass of the object times the square of the speed of the object. Please note, mass is never less than 0, and something squared can never be less than 0. So the kinetic energy is always greater than or equal to 0. I can never have negative kinetic energy. Kinetic energy is kind of like motional energy, and it is a form of energy. Energy stored in the motion of something. We see that energy increases with mass. If I double the mass, I double the kinetic energy. But it depends on v squared. If I double the speed, the kinetic energy actually goes up by a factor of 4. We see this in cars. If you're driving on the road, if you're driving at 30 miles per hour, and you apply the brakes, you might be able to stop in 50 feet, let's say. But if you're driving 60 miles per hour and you hit the brakes just as hard, because you have 4 times as much kinetic energy at 60 miles per hour than you did at 30, the brakes have to do 4 times as much work, and so it's going to have to occur over 4 times as much distance, assuming you hit the brakes just as hard. So you double the speed, but the energy goes up by a factor of 4. It goes up by a factor of 2 squared. Conceptual question. We drop 2 marbles from the top of a building. One marble has twice as much mass as the other. They fall. At the instant before they hit the ground, which of the following is true about the heavier marble? Does it have as much kinetic energy as the lighter one? Is it twice as much, half as much, or is it 4 times as much kinetic energy as the lighter one? Think about it. Again, if you don't know, feel free to ask at the start of next class. Because we have defined kinetic energy the way we have, we can make a direct comparison between the work done on an object and the amount by which its kinetic energy changes. The work is equal to the change in kinetic energy. If you do positive work, you're speeding it up. If you do negative work, you're slowing it down. This equation right here, work equals change in kinetic energy, has some utility, but it's not going to be the final equation. It's a good equation, but it's not the final equation. Let's do an example. We want to slow a 762 kilogram object from 31.1 meters per second to 11.7 meters per second. This is like a car traveling at 65 miles per hour and slowing down to about 20 or 25 miles per hour. How much work is required? So we know the mass, we know the initial velocity, we know the final velocity. The total work done is going to be equal to the change in kinetic energy. The change in kinetic energy is final kinetic energy minus initial kinetic energy. If we assume the mass doesn't change, and that's a safe assumption in this class, then the final kinetic energy is 1/2 mv final squared, and the initial kinetic energy is 1/2 mv initial squared. We know those numbers. We know all of those numbers. We plug them in. 1/2 times 762 times 11.7 squared, because v final, the final speed, is 11.7. Minus 1/2 times 762 times 31.1 squared. Don't forget to square. We get negative 316,000 joules. That sounds like a big number, but we are talking about a car moving at highway speeds. So this is not an unreasonable value. And since the car is slowing down, that by itself should tell you we better get negative work done on the car. Here's a question for you. Watch the video. Oh, yeah, okay. Don't watch the video. So we have a sports car that accelerates from 0 to 30 in 1.5 seconds. How long does it take to accelerate from 0 to 60 if the energy output of the engine is constant? And we're going to ignore friction, especially air resistance. This is perhaps a challenging question. You see the options: 2 seconds, 3 seconds, 4.5 seconds, 6 seconds, 9 seconds, 12 seconds. Think about it. Remember what I said about kinetic energy and its dependence upon speed. And again, if you're not sure what the answer is, feel free to ask next class. That's it. Take care. Bye-bye.